Right, in today's lesson, we're going to look at how to develop and use the formula for the area of a circle. Now, if you follow along with the last three formulas we developed all our formulas based on previous formulas that we already knew. So when we started with our rectangle, we then found the parallelogram because we took that triangle off that side and we made a rectangle out of it. And then our triangle, if I took this triangle with another triangle just like it looked like a parallelogram. And if I took a trapezoid and inverted it upside down with one just like it, then it looked like a parallelogram. So we're able to use previous formulas to find our new formulas. The problem we run into here is, how do I make my triangle look like one of these other formulas? Well, so what we're going to do is we're going to take a look at our circle, and we're first going to divide it into sections. Now I divided it into 8 sections, but we'll talk about what would happen if you had more or less sections than I did. And we're going to take these sections and we're going to remove them. And then we're going to turn them so that we alternate their direction and put them side by side, hopefully so that they match up correctly. Now, if I do that with all of mine, we end up with a shape like such. My 4 purple sections are on the top, with my 4 yellowish or goldish sections down below. Okay. Now, if we look at this, this shape is similar to a parallelogram. As a matter of fact, I could take this shape and slide it right into the parallelogram, and it looks pretty decent. The only complaint, or the only problem with it, is that parallelogram has straight segments going across, and the tops of these aren't perfectly straight. So what I'd like you to do for now is just pretend they were. And then in a second, we'll go through, I'll show you why it's okay to say, all right, within this, we're going to assume that they are. Now, first of all, if this is similar, then we can use this formula, base times height, of this shape here to come up with a formula for a circle. So let's take a look at this shape. Here's my base, this segment right here. Here's my height. Now I'm going to put my chopped up circle back into that spot. And let's take a look first of all at the base. The base is the outer parts of my 4 gold sections. If I go back to my circle, it's the outer parts of the 4 gold circles. Well, what do we call that? Well, it's the distance around, that's circumference, but it's not the whole thing. It's 1/2 of the circumference. And I'm going to move this up a little bit because we're going to need some more room in a second. So that's really my base, the 1/2 of the circumference. My height, or this dotted line from the tip to the end of a section, the dotted line from the tip to the end of the section. So this height is really what we call the radius. So 1/2 of our circumference times our radius gives us this chopped up circle that fits into a parallelogram. Well, let's adjust this now. First of all, we've got a formula for circumference. So 1/2 of the diameter times pi, that all equals circumference, and then we multiply that times the radius. Well, let's see if we can simplify that a little bit more. Well, 1/2 of the diameter is really the same as the radius. So radius times pi times radius. And now rewriting that, I'm simply going to do radius times radius times pi, just rewrote the order of them, and then we can even shorten up radius times radius into just radius squared. So when we look at a formula for the area of a circle of radius squared times pi, and go, how do they ever come up with a formula like that? Well, one way is by dividing up our segments into ways that it can go into a parallelogram, using that parallelogram where the base is 1/2 of my circumference and the height is the radius of the circle. So there's our formula. Now the thing I wanted to show you is, when we talked about those edges being rounded, and said, well, we really can't use that because the edges are still rounded. This is a demonstration to show you how that rounded edge changes depending on how many sections. Now I did mine in 8 sections. We're going to do one in just 4 sections and watch how rounded those tops are. Here's 4 sections. We'll cut it open. We'll slide it together. And you can see, boy, this is kind of like a parallelogram, but definitely not straight, very rounded on the top. Well, let's go back and do it like the 8 sections that we had. And now you'll see that this is a little bit more like a parallelogram, but still pretty rounded on the top, like my example was, pretty rounded. Slide them together. So a little bit more like a parallelogram, but still rounded. Now, hypothetically, we could even cut these things into more sections. So let's go into maybe 20 sections, much more than my 8. And now we cut it into 20 sections, slide them together. And even now that rounded top is even becoming more flat, almost straighter as it appears. And then the most that this allows us to do is up to 30. So we'll do that just to demonstrate. But by the time we cut that circle into 30 sections, you'll notice that our segments now are really pretty darn straight, pretty close to what a parallelogram would look like. Can you imagine if we cut it into 500 sections? Those sections at the top would be so narrow that they'd almost be perfectly straight. Now, that doesn't change our formula. This base on the right is still half of the circumference. Let me see if I can get my tools to work here and so I can demonstrate that. This right here is still half the blue parts, which would be half my circle. This distance right here is still the radius of one of my circles. So we still have 1/2 of the circumference times the radius, which still is 1/2 of diameter times pi times radius, which is still the same as radius times pi times radius, which is still radius squared times pi. So it doesn't matter how many slices you cut it into. Matter of fact, the more you cut it in, to the more exact it'll actually become like a parallelogram. Okay. All right then, a couple quick practice problems. I'll let you try these quickly and then I'll go through their solutions. Remember, the key is we don't want to use diameter. We need radius. So you need to find that radius first. If you don't know it, you got to find it by taking the diameter and cutting it in half. So in this first picture, even though they give us a diameter of 45, we need to be using a radius of 22.5. Okay. So r squared times pi. Here they give us r, so r squared times pi. All right, the first one is 22.5 squared times 3. Mistake of mine. 22.5 squared times pi is 1589.6, and we want to label this with square feet. Now, I use 3.14 for pi. If you use the pi button, you're going to be around 1590 point something. So depending on what you use for pi. Here, 12 squared is 144, and 144 times pi is about 452.1, and this would be inches squared. Again, if you used the pi button instead of 3.14, you're going to get an answer slightly different than the one I put up there. But again, it really doesn't matter which one you use. They're both pretty good estimates for pi. Just a reminder, we kind of talked about a problem like this the other day, that if I wanted the area of this purple part, you got to find the area of the large section first, which is a trapezoid. And you also may have to look back at your formula for that. Find the area of the circle in the middle, and then subtract those, remove those away. Assignment from you for tomorrow is on page 322. Now, the same page we just did yesterday. Matter of fact, the first problems are the exact same problems, 9 through 18, except now we are finding the area only. Where yesterday we looked for the circumference. Okay. I'd also like you to do numbers 27 through 30.